Hello everyone, welcome to this lecture on solving linear homogeneous recurrence equations, part 1. So just to quickly recap, in the last lecture we discussed how we can solve counting problems by formulating recurrence equations, and we also started discussing about how to solve the recurrence equations, because when you want to count a certain number of things using recurrence equations, then there are two parts. First thing is formulating the recurrence equation, and the second thing will be to finding the closed form formula or the solution for the recurrence equation, because until and unless you don't have a closed form formula, you may not be able to come up with a solution, right? You have to solve the recurrence equation. So we already discussed a category of simple method, namely the iterative method, in the last lecture. And in this lecture, we will continue our discussion regarding solving linear homogeneous recurrence equations. And we will discuss one category, namely when we have non-repeated characteristic roots. So just to quickly recap what exactly are linear homogeneous recurrence equations of degree k. The general form is this. You have an infinite sequence where the nth term of the sequence depends upon the previous k terms, in the sense that the dependency on a of n minus k for a of n should be always there, which is stated or which is imposed by this condition, namely ck should not be 0. And these are so this is an example of this Fibonacci, the recurrence equation for the Fibonacci sequence is an example of linear homogeneous equation. This is a nonlinear equation and this is a non-homogeneous equation. Okay, so we are interested to come up with a general method for solving recurrence equations of this type. So I will first demonstrate the process, assuming that we have a linear homogeneous recurrence equation of degree 2. Okay, when I say degree 2, that means the nth term of that infinite sequence, which I'm interested to find out, depends upon the previous two term. Namely, it depends on a of n minus 1 and a of n minus 2, where c2 will be not 0. c1 can be 0, but c2 definitely cannot be 0. And you may or may not be given initial conditions. So again, recall in the last lecture, we discussed that if you are not given initial conditions, then there could be multiple number of sequences or solutions satisfying the recurrence condition, because since the initial conditions are not given, you are free to put any value as the initial condition, any term as the initial condition. And if once you freeze that initial conditions, that determine what will be the remaining terms of the sequence, right? So in this case, I am assuming that you are given the initial conditions. Say the initial conditions are the zeroth term or the starting term is v0, and the first term in the sense a of 1 is v of 1. So this is not first term, this is actually the second term, but in terms of index, it is a of 1. So the first step here will be to construct what we call as characteristic equation. And the characteristic equation will be an equation in an unknown r. So r is a variable here. R is an unknown variable here. Unknown in the sense its value is not known. So this characteristic equation will be a quadratic equation of quadratic equation in R. Why quadratic? Because right now we are considering degree 2 recurrence equations. Okay, and the form of the characteristic equation will be this: r square minus c1 times r minus c2 equal to 0. So that's why it's important that your recurrence condition should be of this form. Okay. Now, since this is a quadratic equation, all right, we will have two roots for these equations. So I call those roots as R1 and R2. And those roots are called as characteristic roots because they are the roots of this characteristic equation. Now, there could be two possibilities that the roots R1 and R2 are distinct. That means they are different. And the second case could be that they are same. And when I say non-repeated roots, so we will I mean the first case, right, the former case, where the roots R1 and R2 are different. So once you have solved the characteristic equation, you will have the value of the characteristic roots and you can check whether you are in this case or not. Now, if we are in this case, then we can prove the following. We can prove that any sequence which is a solution of the recurrence equation that is given to you will be of this form. Okay. So for the moment, imagine that you are not given the initial conditions. Imagine these initial conditions are not given. You are just interested to find out one possible sequence satisfying the given recurrence condition. Then what this theorem says is any sequence, any infinite sequence whose nth term satisfies this recurrence condition will have its nth term of the form alpha 1 times r1 power n plus alpha 2 times r2 power n for some arbitrary constants alpha 1 and alpha 2. Okay, that's what the theorem says. And now, if you are given these initial conditions, that means you are interested to find out the sequence whose initial terms are v0 and v1 as well, then the exact values of these constants alpha 1 and alpha 2 can be obtained by utilizing the initial conditions. Okay, so let's first prove this theorem statement here. So what are the things which are given to you? Your goal is to find out a recurrence. Your goal is to find out an arbitrary sequence whose nth term satisfies this recurrence condition. You have found the characteristic equation. You solved the characteristic equation and the roots are distinct. And our goal is to prove that any sequence, so this is an arbitrary sequence here. Our goal is to prove that you take any arbitrary sequence whose nth term is of this form, some constant times r1 power n plus another constant times second root power n. Then our goal is that if a sequence is of this form, then indeed it satisfies the given recurrence condition. So let's prove that. And this is true uh, irrespective of the initial conditions, mind it. That means what we are trying to prove is it doesn't matter what are the initial conditions, the nth term of that sequence will be of this form. So let's prove that. And the proof is very simple. So what is the nth term of the sequence, arbitrary sequence that we are considering? Uh, or put it another way, our goal is to show that if the nth term is of this form, then this recurrence condition is satisfied. So let's prove that whether indeed it satisfies this recurrence condition or not. So what is the recurrence condition? The recurrence condition says that C1 times the n minus 1th term of that arbitrary sequence plus C2 times the n minus 2th term of that arbitrary sequence should be equal to the nth term of this arbitrary sequence. That's what we have to prove. So let's prove that. So this will be the n minus 1th term of the arbitrary sequence. How do we obtain this? By substituting n minus 1 in this formula, right? So the arbitrary sequence that we are considering, its nth term is of this form. So its n minus 1th term will be alpha 1 times r1 power n minus 1 plus alpha 2 times r2 power n minus 1. And its n minus 2th term will be this. Again, just obtained by substituting n equal to n minus 2 in that in the formula for the nth term of the sequence. Now we will solve it. So we will rearrange the terms, and after rearranging the terms we get this. And now what we are going to do is we are going to utilize the fact that R1 and R2 are the roots of this characteristic equation. That means both R1 as well as R2 satisfies this condition. That means R1 square minus C1 times R1 minus C2 is equal to 0, or in other words, R1 square is C1 times R1 plus C2, right? So that's why I can substitute this part by R1 square. And similarly, your R2 also satisfies the characteristic equation. So we also have R2 square minus C1 times R2 minus C2 equal to 0, which in other words implies C1 times R2 plus C2 is R2 square. So by substituting this, we get the following. And what is this? This is nothing but the nth term of the arbitrary sequence. And we have proved the part 1, right? So we have shown that you take any arbitrary sequence, if its nth term is of this form, then definitely that satisfies the recurrence condition. Okay. Now you can have any constant alpha 1 and alpha 2, right? It's up to you. You put any constant alpha 1, alpha 2, that will give you an arbitrary sequence or a sequence which satisfies the given recurrence condition. So I can have alpha 1 and alpha 2 to be say 1 comma 1. That will give me one arbitrary sequence satisfying the given recurrence condition. I can put alpha 1 alpha 2 to be say 0 0. That also will be satisfying the recurrence condition, and so on. Okay. In fact, arbitrary sequence where all the terms are 0, right? Forget about the initial conditions. That trivially satisfies the recurrence condition, but uh, we are interested in uh, we are not interested in such trivial solutions. Okay, so this proves the theorem in one direction. That means you know how to find out at least one sequence satisfying the recurrence condition. But the theorem statement is an if and only if statement. It basically says that if at all there is a solution, then it has to be of this form, where the nth term is some constant times r1 power n plus another constant times r2 power n. We had shown right now that you give me a sequence whose nth term is of this form, namely alpha 1 times r1 power n plus alpha 2 times r2 power n. It will satisfy the uh, uh, recurrence condition. But now I want to prove the other way around, that if at all there is would have been a solution, the structure of the nth term of that solution will be constant times r1 power n plus another constant times r2 power n. So that will be the part 2 of the proof. Okay. So now here we are assuming that suppose there is some solution satisfying this recurrence condition and the initial conditions that are given to you. Then we want to prove that this nth term of the sequence is of this form for some constants alpha 1 and alpha 2. And the proof strategy here will be as follows. We will first prove that you take another sequence different from the sequence that you are considering right now, or the solution that you are considering right now. So I am taking some another sequence whose nth term is of this form. Then I will show that it satisfies not only your recurrence condition, but it satisfies the initial conditions as well. If I prove that, assuming that, so this is what I will show. So this is the goal and this is my claim. Assuming my claim is true, it automatically implies that the arbitrary solution, right, that you are considering, its nth term is also of the form some constant times r1 power n plus some constant times r2 power n, where the constants are this. And why so? This is because I can't have two different arbitrary sequences satisfying the same recurrence condition and having the same initial conditions, right? As per my claim, I have one sequence satisfying the recurrence condition as well as the initial conditions, and I am also given another sequence which also whose structure I don't know, right? Whose A of n I don't know, which also satisfies the recurrence condition as well as the same initial condition, same two initial condition. Then, as we discussed in the last lecture, if I want to satisfy simultaneously the initial conditions as well as the recurrence condition, then there can be only one possible sequence. You can't have multiple possible sequences whose terms are different, but they are satisfying the initial conditions as well as the recurrence condition. That can't happen, right? Because if the initial conditions of the two sequences are same, then that automatically implies that all the following terms of the sequences are also going to be the same because both of them satisfies the recurrence condition. So assuming my claim is true, I end up showing that the arbitrary solution whose nth term I don't know is of this form: constant times r1 power n plus constant times r2 power n, because as per my claim there is another sequence whose nth term is v1 minus v0 times r2 over r1 minus r2 times r1 power n. So this is my constant and this is my second constant, and that satisfies the recurrence condition as well as the initial condition. By the way, the reason I am highlighting this r1 minus r2 here in the denominator is that these constants r1 and these constants alpha 1 and alpha 2 are well defined. Even though in the denominator I have r1 minus r2, this is because I am considering the case where r1 and r2 are distinct. And if r1 and r2 are distinct, their difference will not be zero. That's why the constants alpha 1 and alpha 2 that we are considering in this proof are well defined, right? So what is left now? We are now left with showing this. We have to now show this claim. We have to prove that this claim is true. So let's prove this claim, right? So here we are given some arbitrary solution for the recurrence condition as well as satisfying the initial condition. We have to prove that if that is the case, then the nth term of that arbitrary solution is of this form. For that, we first observe that from the proof of the part 1 of this theorem, you take any sequence, doesn't matter what is the initial condition, you take any sequence whose nth term is of this form: some constant beta 1 times r1 power n plus some constant times r2 power n, it always satisfies the recurrence condition, right? This is what we proved in the proof of part 1. Okay, and now if you want this sequence whose nth term is capital A of n, right? So to differentiate this sequence from the sequence whose nth term is small a of n, I am using the capital A here, right? So the term whose nth term is capital A of n, that is a sequence which is different from the arbitrary solution whose nth term is this small a of n, right? The nth term of the sequence whose nth term is beta 1 times r1 power n plus beta 2 times r2 power n is denoted by this capital A of n. Okay, we know that this satisfies the recurrence condition. That means we know that A of n, the capital A of n, is indeed c1 times capital A of n minus 1 plus c2 times capital A of n minus 2. We know this. This comes from the proof of part 1. Same thing that we did. We utilized that R1 is a characteristic root, R2 is a characteristic root, and substituted R1 square with C1 times R1 plus C2 and so on. The same proof is applicable here. Now, if I want to find out the initial terms of that capital A series, right, we would like that A0 term, the capital A0 term should satisfy V0 and capital A1 term should satisfy V1, right? If that is the case, then I get two equations in beta 1 and beta 2. How? If I substitute n equal to 0 here, I get one equation, and if I substitute n equal to 1 here, I get another equation. So now what are the things known to me? V0 and V1 are already given to me because they are part of the initial, they are the initial conditions. Beta 1 and beta 2 are the unknowns, right? And R1 and R2 are known to you. So you have now two equations in two unknowns, and you can solve them and get the value of beta 1 and beta 2. That means what I am now, what I have done now is I have now found a concrete sequence, namely the capital A sequence, whose nth term is beta 1 times R1 power n plus beta 2 times R2 power n. I know it satisfies the recurrence condition, and I also know the values of beta 1 and beta 2 for which this capital A series will satisfy the given initial conditions. Namely, I know the values of beta 1 and beta 2 for which A, capital A of 0 would have given me V0, and capital A of 1 would have given me V1. I know that. Okay. So our goal was to prove this claim. Okay. And we proved it. We proved that indeed any capital A sequence, a sequence whose nth term is this, satisfies the recurrence condition as well as the initial conditions V0 and V1. Okay. What this means? This means that now I have two different sequences, a capital A sequence satisfying the recurrence condition as well as the initial condition, and the arbitrary solution which I assumed satisfying the given recurrence condition as well as the initial conditions, right? And now both these two sequences are same because as I said earlier, I can't have two different sequences with the same initial conditions. I stress with the same initial conditions but different nth term. That can't happen, and simultaneously satisfying the recurrence condition. That can't happen. If you don't put restriction on the initial conditions, if I don't put the restriction that their initial conditions are same, that means if I have sequence A and I have sequence B whose initial conditions are different but nth terms are different, and satisfying the recurrence condition, that's possible. But I can't have two different sequences, A sequence and B sequence, whose initial terms are different. They satisfy the recurrence conditions, right? Uh, whose initial terms are same and nth terms are different, but simultaneously satisfying the recurrence condition. That's not possible, right? So we have now a capital A sequence, we have now a small a sequence. Both of them are satisfying the recurrence condition, and both of them are satisfying the initial conditions. So that's possible only when your capital AN is equal to small an. That means the arbitrary solution that you considered here, it's from the form some constant times R1 power n plus some constant times R2 power n, because that is the general, because that is the inner term of this capital A sequence. Okay. So that completes the proof for the part 2 here. So now, till now we focused on the case of degree 2, right? Now we will try to extend or generalize this theory for the case of degree k linear homogeneous recurrence equations. So remember the degree k equation, the general formula is this, where ck is not allowed to be 0, and you may or may not be given the initial conditions. If you are not given the initial conditions, then you will stop with showing the closed form formula for the nth term. in terms of some arbitrary constants. Those constants you can put as any constant. But if you are given the initial conditions as well, then you can solve and find out those concrete constants. Okay. So what will be the process in the general case? We will first form a characteristic equation. This will be a degree k equation. Okay. Next, we will solve it and find out characteristic roots. So let us denote the characteristic roots by R1, R2, and Rk. Now, there could be multiple cases. The case that we considered when k was 2 and that we are going to consider in this case is the case of distinct roots. Namely, when all your k characteristic roots are different. Then, extending the theorem that we proved for the case of k equal to 2, we can show that any sequence, right, which satisfies this recurrence condition will have its nth term of the following form. Some constant times r1 power n plus another constant times r2 power n, and continuing like that, some constant times rk power n. Okay. This will be the general form of the solution satisfying the recurrence condition. The exact values of these constants alpha 1, alpha 2, alpha k can be obtained from the initial conditions. So if you are given the initial conditions, then by substituting n equal to 0, n equal to 1, n equal to k minus 1, we will get k equations in this k unknowns alpha 1 to alpha k, and then we can get the concrete values of the constants alpha 1 to alpha k. But if you are not given the initial condition, then the only thing that we can do is we can just find out the general form of the solution. It's up to us what constants alpha 1, alpha 2, alpha k we substitute. That will determine the sequence satisfying the given recurrence condition. But if you want a unique solution, then you also need to have the initial conditions available with you. Okay. So now let's see an example for the method where we will apply the method that we have discussed. We now want to find out an explicit formula for the nth term of the Fibonacci sequence. Okay, so just to recall, the nth term of the Fibonacci sequence is the following. Okay, the nth term depends on the previous two terms, and the initial conditions are this. Okay, so the first step will be to find a characteristic equation. So here your C1 is 1, your C2 is 2, C2 is also 1, sorry. So that's why our characteristic equation will be of this form. Now if I solve the characteristic equation and find the characteristic roots, then I see that I obtained two distinct roots. That means I can apply the theorem that we have discussed in this lecture. What I will say is that the nth term or any sequence whose nth term is of this form will satisfy the recurrence condition, right? It may or may not satisfy the initial conditions, but it will satisfy the recurrence condition. And the recurrence condition is triggered from n greater than equal to 2 onwards. That means what I am saying is, I don't know what is the first term or the zeroth term. I don't know what is the first term in the sense, I don't know what's the second term, sorry. And then I know that uh, from next term onwards, anything of this form satisfies the recurrence condition. That's what I am saying here. Now, it's up to me, whatever value for alpha 1 and alpha 2 I substitute, that will determine a different Fibonacci sequence, right? So if the initial conditions of the actual Fibonacci sequence are not given, if someone just gives me this recurrence condition, if these are not given to me, if someone gives me just this recurrence condition and want to and ask me find out the sequence satisfying this recurrence condition, I can say that okay, any sequence whose nth term is some constant time 1 plus root 5 over 2 power n plus some constant times 1 minus root 5 over 2 power n will satisfy the recurrence condition without worrying about what are the first two terms. It could be any two terms obtained by substituting different values of alpha 1 and alpha 2. But in this case, I am given the initial conditions, right? So if I am given the initial conditions, I will utilize them to find out the exact value of alpha 1 and alpha 2, which is consistent with the initial conditions of the actual Fibonacci sequence, right? So I am interested to find out the sequence whose zeroth term is 0 and the next term is 1. That means I have to substitute n equal to 0 and n equal to 1 in this general formula. And then I will get two equations in alpha 1 and alpha 2, and by solving them, I can get the exact values of my constants alpha 1 and alpha 2. They will be 1 plus 1 over root 5 and minus 1 over root 5. And then I will say that, okay, here is the exact solution of the actual Fibonacci sequence, which satisfies not only the initial conditions, but also the recurrence condition. Okay. So that brings me to the end of this lecture. These are the references for today's lecture. Just to summarize, in this lecture, we started discussing about how to solve linear homogeneous recurrence equations of degree k. And we saw one of the cases, namely we saw the case where the characteristic roots are distinct. Okay, in this case, we saw how to find the characteristic root, and if all the characteristic roots are different, then we know what will be the general solution. And depending upon whether the initial conditions are available or not, we can find out the exact solution. Thank you.